In the last class, we discussed shift register. In that, to be very specific, we discussed serial input, serial output, shift register. Okay. So in today's class, we will be discussing parallel input, parallel output, shift register, and further topics. I hope I am audible and the presentation is also visible. Can someone reply in the chat window? Okay, thank you, Varsha. So next is parallel data inputs and parallel data output shift register. Here, if you observe, we are using all D flip-flops and this is clock. Look here, we are able to give inputs in parallel. That means D3, D2, D0, D1, D2, D3, we are able to access in parallel and load it. And similarly, we are able to get the output Q0, Q1, Q2, Q3 simultaneously from all the flip-flop. That's why we call it as parallel data input and parallel data output. Okay, essentially it is 4-bit parallel in and parallel out. Okay, so the next thing is shift register implemented using muxes and D flip-flops. Okay, we call it as universal shift registers. The symbolic representation of this universal shift register is as follows. So look here. So in this rectangle, what we have written 4-bit parallel in, parallel out shift register. So to indicate. Okay. And I am indicating inputs through D0, D1, D2, D3, parallel input. And what are all the outputs? Q0, Q1, Q2, Q3 are outputs. Okay. And look here, we have serial output. That means what? This particular shift register is acting as both parallel in, parallel out, serial in, serial out, serial in, parallel out, parallel in, serial out. In all possible way, it can act. Okay. So here, so that's why we have shift enable, load enable, and clock. And if you observe, there is a bubble in the clock which indicates it is falling edge triggered shift register. Okay. Whether the presentation is visible, because I'm not seeing that symbol. You are presenting this. Whether it is...
Yes, ma'am.
Okay. Okay. So observe here, very important. You have serial in and serial out, parallel in and parallel out. So it can act as serial in, serial out, parallel in, parallel out, serial in, parallel out, parallel in, serial out. All possible ways it can act. Single, that's why we call it as universal shift register. And look here, you have, whenever shift is 0, load is 0. These two signals or these two inputs are 0. What will happen? Nothing will happen. Whatever the present state, that will be the next state. So Q3 plus, Q2 plus, Q1 plus and Q0 plus will be same as that of Q3, Q2, Q1, Q0. So what is the action that happened? No change. And similarly, when shift is equal to 0 and load is equal to 1, what happens? Loading will happen. Loading will happen. That means what? Whatever D3, D2, D1, D0 is there, that will be copied to the D flip-flop. Okay. And so D flip-flop which is present in the shift register. And that's why next state will become whatever the inputs you are giving, D3, D2, D1, D2. So what is the action that we performed? Load is the action that we performed. Similarly, what happens? When shift is equal to 1, this is very important, observe here, whatever may be the value of load, if it is 1 also, the priority will be given to the shift register only. So when shift is 1, whatever may be the value of load, whatever you are giving in as serial input, that will be copied to D3 and reflected as Q3. Whatever the Q3 will be given to Q2, Q2 will be given to Q1. So what happened actually here? Right shift happened. Okay. So this is the symbolic representation of the universal shift register, and this is the truth table or next state table. Okay. So could you understand this much? Very important. Till here, everybody could understand. Please reply fast. I didn't tell anything very tricky. It was very self-explanatory. Okay. Okay. So let us continue. Okay, whatever the register I showed just now can be implemented using D flip-flops and mux. So you are already familiar with the working of mux. Okay, so this kind of operation should happen in our implementation. So how to ensure this kind of operation will implement? Okay, look here, I have 4 D flip-flops, 1, 2, 3 and 4. For each of them, instead of directly connecting to D, I am connecting a 2 to 1 mux, 2 to 1 mux. So look here. So what is my intention? Whenever this both S and shift and L are 0, no change should happen. So that's why what I am doing, whenever this, look here, shift and L, that is load, are giving a selection lines to this particular multiplexer. Observe here, very important. This is given as selection line to this particular multiplexer. So when it is 0, 0, the first one will be selected and it will be given to D. Okay, so first one, what should be connected to the first mux input? I will connect output of the D flip-flop itself. Why? Because when SH is equal to 1 and L is equal to 1, I do not want any change to happen. That's why students, for this mux, the first input will be Q itself. Same thing is done here. Same thing is done here. Same thing is done here. So whenever it is 0, 1, what should happen, students? Loading should happen. That's why what I will do, for the second input of the mux, I will connect the respective inputs. For the first mux D0 as the second input, for the second mux D1 as the second input, for the third mux D2 as the second input, for the fourth mux D3 as the second input. Okay. Now, what should happen for one don't care? That is, for both combination 1 0 and 1 1, same action should happen. That's why I'm combining 1 0 and 1 1. You can observe this line. I'm combining 1 0 1 1. 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 In this case, what should happen? Actually, shifting should happen. That's why what I'm giving, I'm giving SI to the last flip-flop and last flip-flop's output to the last but one flip-flop. That's its output to the next flip-flop. Its output to the next flip-flop. Like this, we are ensuring that using 2 to 1 mux and D flip-flop, we are implementing universal register, shift register. So what we are giving, we are considering output of the mux as input to the each flip-flop, and first input to the first input mux is nothing but its own output. Second is data to be loaded. For third and fourth, output of the previous flip-flop. And for the first flip-flop, I am giving serial input as the input. Okay, so this bubble indicates it is falling gets triggered D flip-flop. Okay, I hope you are following. Same thing is written here. Okay, the implementation details. When it is 0 0, what is happening? No change. When it is 0 1, what is happening? Whatever the data is getting loaded. When it is 1 0, what is happening? Shifting, right shifting is happening. For 1 1 also right shifting is happening. So whatever I have written here, same thing is rewritten here. Okay, so based on this, I will be able to write the equation. How I will be able to write the equation? See, for Q3, we have written equation like this. Okay, so what is Q3, students? Q3 is nothing but SH dash ANDed with L dash ANDed with Q3 okay, plus sh dash ended with L, because L is 1 here, ended with D3 plus sh L dash and SI. Okay, so here actually L we need not consider, because if you combine these two, you will get SH SI only. Similarly, we are obtaining equation by ANDing each of the expression and ORing together. Okay, Q2 plus is SH dash L dash Q2 plus SH dash L D2 plus SH and Q3. Okay. Similarly, you can obtain for Q1 dash and Q naught plus. These are the equations. Next state equations. Okay. Um, okay. Could you follow this much, students? Are you able to follow universal shift register and its next state equation and whatever the circuit diagram we have written it using mux? Okay. Thank you. Okay. Assuming that the register is initially clear. Clear means all set to 0 and serial input is also 0 throughout. We are going to write the timing diagram and data to be loaded as 1011. You can give, you can expect this kind of question. Assuming that this the initial value is this, serial input is this is the data to be loaded, write the timing diagram. So that's what is written here. Look here. Initially load is equal to 1, shift is 0, and this is the value of D3. Okay, what will be the value of Q3? So look here, Q3 became, okay, at one clock cycle, since it is parallel in whatever the value of D0, D1, D2, D3, 1011, that got loaded to the Q3, Q2, Q1, Q0. Understanding, since load was 1, for the next clock cycle, everything, whatever the value of D0, D1, D2, D3 got copied to Q0, Q1, Q2, Q3. Now you look, only shift is high, load is low. This is low, load is low. So what is happening, students? So shifting will happen. Okay. We assumed here SI to be 0. So what will happen in the place of Q3? SI will come and sit in the place of Q2. Q3 will come and sit in the place of Q1. Q2 will come and sit in the place of Q0. Q1 will come and sit. So shifting has happened. Okay. Once again, the shifting is happening. Okay. SI is 0. Okay. Last bits we are losing. Here 1 we lost. Here once again 1 we lost. Now we will lose 0. Look here. Okay. But here once again the shifting is becoming 0. It will be retained with the same value. Same value will be retained. So look here, there is no change for, in the value of Q3, Q2, Q0, Q1, Q0 here and here. So this timing diagram shows whenever the initial state of the Q3, Q2, Q1, Q0. Look here at the time of 0. All are 0 only. And we just copied D3, D2, D1, D0 into Q3, Q2, Q1, Q0 because L was 1. And after that shift signal became high, so shifting is happening. At what time, till what time shifting will happen? Till the shift signal is high. Okay, same thing is explained here. Okay, okay, students, could you understand shift timing diagram? Timing diagram, could you understand? Very simple. Can you please reply? Timing diagram. Didn't understand? Reply fast, students. You could not understand? Something you reply. See, it is very simple. We are assuming that the initial value of the shift register is 0, 0. This is having 0 value, 0, 0, 0. And the serial in is 0. Okay. This is also 0. This is also 0. This is also 0. This is also 0. Okay. And then D3, D2, D1, D0 is 1, 0, 1, 1. Okay. So D3 is 1, 0, 1, 1. So if L is equal to 1, what happens? D3 will be copied to Q3, D2 will be copied to Q2, D1 will be copied to Q1, D0 will be copied to Q0. That's what is happening here. Now L is high, this value is 1011 is getting copied here. That's all. And after that, shift is becoming high. Look here, shift is high. So what happens? The S in is 0. That will get right shifted. SI will come and sit in Q3, Q3 will come and sit in Q2, Q2 will come and sit in Q1, Q1, the previous value of Q1 will come and sit in Q0. And that will get, the process will get repeated. Till what? Till shift is high. That's all. That's what is told in the timing diagram. Okay. Same thing is explained here. Now, we are going to one more topic. A circuit that cycles through a fixed sequence of state is called a counter. Okay, we are actually introducing counter in the shift register topic only. Okay, a circuit that cycles through a fixed sequence of state is called counter. Like for example, if the circuit is giving the output 1, 2, 3, 4, and then again 1, 2, 3, 4, it is repeating 1, 2, 3, 4. I can call it as a counter. There is no condition that it should count continuously, but generally it counts continuously. But what is the condition? It should go through fixed sequence of state. Okay. A shift register with, look here, a shift register, I'm considering shift register only, with non-inverted feedback is known as ring counter or cyclic shift counter. Same shift register with inverted feedback is called Johnson counter or twisted ring counter. Okay, I'll show you. Look here. Here, you do not analyze much. You simply see this is a shift register, right? You have, this is a shift register. Okay, in this shift register, what is happening? This output Q3 is there, no? That is fed back here. Okay. So whenever you are feeding back Q3 to the first flip-flop, we are going to call it as ring counter. Similarly, here, inverted output, that is T bar, is given as feedback. That's why it is called as Johnson counter. Look here, normal output, if it is given as feedback, ring counter. Inverted output, if it is given as feedback, that is Johnson counter. That's what is written here. I'll repeat. A circuit that cycles through a fixed sequence of state is called a counter. A shift register with non-inverted feedback is called as ring counter. Non-inverted feedback na kotre feed first flip-flop we call it as ring counter or cyclic shift register. Inverted feedback na kotre Johnson counter ಅಥವಾ twisted ring counter ಅಂತ ಕರೀತಾರೆ. You should be knowing this. Okay. ಸೊ ಅರ್ಥ ಆಯ್ತಲ್ವಾ? ರಿಂಗ್ ಕೌಂಟರ್ ಅಂದ್ರೆ ಏನು, ಜಾನ್ಸನ್ ರಿಂಗ್ ಕೌಂಟರ್ ಅಂದ್ರೆ ಏನು ಅಂತ ಗೊತ್ತಾಯ್ತಾ? ರಿಂಗ್ ಕೌಂಟರ್, ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು. ಓಕೆ, okay, let us consider this ring counter. This ring counter is developed by 4D flip-flops. Actually, basically it is a shift register. Okay, initially what happens? Initially the value is 1000. Next it is 0 1 0 0 0 0 1 0 0 0 1. Like this, the output is getting changed. Again, it is becoming 1 0 0 and it is repeating. Okay. So look here, initially this is Q naught. This is 1 0 0 0. What happens here? You will give this 0 to this again. Actually, it is a shift register, right? It will shift. Only shifting is happening. Look here. 1 0 0 0 1 0 0 0 0 1 0 0 0 1, and again whatever the last is there that you are giving as feedback, so 1 0 0 0. So it is counting from this number to this number. Okay, it is we can call it as okay, so it is fixed set of, as in this definition, a circuit that cycles through a fixed sequence of state is called counter. So what is fixed sequence here? It will always sequence from 1 0 0 to 0 1 0 0 will be the second, 0 0 1 0 will be the third, and 0 0 0 1 will be the next. It will be cycling through these states only. That's why we call it as counter. Okay. And similarly, we have Johnson counter. In Johnson counter, what happens? Like if you start it from here, you are using D flip flop, and if you start it from all zeros, it will change to 1 0 0 0 1 1 0 0 if serial in is 1. Okay. Like look here, because of the circuit only, all one, when all ones becomes, if you observe here, we have connected what? We have connected the inverted output as input here, inverted output as input. So it will become 0 here. So shifting, again shifting will happen. Again, its inverted output we are connected here. Okay, so it will repeat. So it is just for the idea. Now you just remember only this much. Ring counter means non-inverted feedback will be connected. Johnson counter means inverted feedback will be connected. That much is enough. And the definition of the counter. What is the definition of the counter? The circuit that cycles through a fixed sequence of states. Fixed sequence of states. Need not be continuous, but usually it will be continuous. Okay, but this is important. These two things we will revisit later, but this is important. This one is important. So look here. Here 3D flip-flops are there. 3D flip-flops are there, which are acting as shift register. Okay. And the inverted feedback, this inverted feedback is connected. That's why you call it as Johnson counter or twisted ring counter. If you assume, you just assume, initially you have all zeros. This is also 0. This is also 0. This is also 0. Then what happens? Since you are giving inverted as feedback, you will receive 1 here. So what happens? It will become 1 0 0. And this 1 will be passed here. Okay, it is again receiving 1. So it will become 1 1 0. Next it will become triple 1. When it becomes triple 1, here you are going to give 0. So it will become 0 1 1. And again 0 0 1. And again 0 0 0. So it will keep on continuing in this only if you assume it starts from triple 0. Okay. So, but one thing, if the initial state is 0 0, the initial value of D3 is 1. So after that clock pulse, the register state is 1 0 0 and it continues. But if the initial state is 0 1 0, if the initial state is 0 1 0, can you tell me what happens? If the initial state is 0 1 0, what happens? 0 1 0. So here 1 will be fed back. So it will become 1 0 1. So 1 will be fed back. So it will receive 1 here. And it will become 1 0 1. Okay. So what happens if it is in 000 state? It will act as this counter. And if it is in 0 1 0, what happens? You observe the 010 and 101 are not there in this particular loop. Okay, if it by chance if it comes to 010, okay, we will have the secondary loop. We will have the secondary loop. This is okay. It will simply shift from this to this. Okay. So this is about Johnson counter. Next thing is general shift register counter. Okay. So this is the general representation of shift register counter. This figure shows general form of shift register. Okay, where the bit is being shifted into the leftmost stage can be a general function of the shift register contents. That means what? You have some gate logic here. Gate logic here. This gate logic will be taken input from this parallel output of this shift register. Okay, and it will be given as serial input. I'll repeat, you may be having some shift register. Its parallel output will be considered as input to some gate logic, and then you will use it as serial input. Okay, if the gate logic contains only exclusive OR gates, we call it as linear shift register. Okay, for each integer n, there exists a linear n bit shift register. If you have one integer, 1 bit shift register. Okay, and generally it will be having the count cycle of length 2n minus 1. Okay, all states are included except for the all zero state. This is the general operation. Linear shift register counters have many applications. Random number generator in higher studies or in your higher semesters, you will come to know about random number generator for data security. Many applications are there. For that, we can use this shift register. Okay, so whatever we discussed in this class, let me summarize. We discussed what is parallel in parallel out shift register. This is the example for parallel in. You are parallelly loading the data and parallelly taking out the data. Parallel in parallel out shift register. And then we discussed universal shift register. We discussed universal shift register wherein you can do serial in serial out, parallel in parallel out, serial in parallel out, parallel in serial out. And we deduced, like we written the circuit diagram using mux, and we deduced the equation for this universal shift register. And we also written the timing diagram for this particular shift register. Okay. After this timing diagram, we also discussed what is counter. Counter is what? It should go through fixed sequence of states. Need not be continuous, but generally it will be continuous. And if you are making the counter by giving the feedback of non-inverted feedback of the shift register, you call it as ring counter. If you are giving inverted feedback, you call it as Johnson counter. So that is given here. If you here you are giving non-inverted feedback, that's why it is called as ring counter. Okay. And here you are giving inverted feedback, that's why you call it as Johnson counter. So here we are having the example of Johnson counter, wherein you are using 3D flip-flops. Okay, if it is initially in the state 000, it will come to 100 state, 110 state, 111 state, 011 state, 001 state, and again 000. Okay, and this will continuous. The looping will continuous. But if you observe that there is no state 010 here. 010 is not present here. Okay, 010 is not present here. Okay, if it encounters 010 state, it will give rise to secondary loop as it will make the circuit to stay in one more state, that is 1 0 1, and from 101 again it will go to 0 1 0. You can observe here, if it is in 0 1 0, here inverted is given, so 1 0 1. Okay, so this is primary loop and this is secondary loop. Okay, and general representation of shift register counter is something like this. Okay, here you have n bit shift register and you have serial input. In Johnson counter and ring counter, the feedback was given from the inverted or non-inverted output. But generally what happens, we will have some gate logic, and through for the input for this gate logic is output of this parallel output of this shift register, and its output is given as serial input. If this gate logic contains only exclusive OR gates, we call it as linear shift register counter. For each integer n, there exists n bit shift register counter that generates 2n minus 1 count cycle length. Okay, the cycle length will be 2n minus 1. Here all states are included except all zeros. Okay, so it will be having many applications. Random number generator. Okay, why do we need random generator? For encoders and decoders. Okay, these encoders or decoders are not the encoders and decoders what we studied. If you Google encoders and decoders, not ADE one, you will be having some error correcting codes in the network. Whenever you are sending some data, usually some packet loss will happen. When packet loss will happen, the packets will not reach properly, the data packets. For that correction, we will use random number generator. For that, the shift registers can be used. So whatever planned for today is completed. I hope you have understood. From next class, I will be doing design of binary counters. So for this, for you have to prepare and come for tomorrow's class. You should be knowing the truth table of all the flip-flops. Okay, for tomorrow's class, you should be knowing truth table of all the flip-flops. So if you have any doubts, you can put it in the chat window, or you can unmute yourself and tell me and enter your attendance simultaneously. As I said, for tomorrow's class, you should be knowing truth table of all the flip-flops.